We have spoken in great length about functions that are continuous over an interval and the fact that we can make this line called the secant line to describe the average rate of change of the curve over the interval. So we've said that the slope of the secant line could be constructed as simply rise over run, or the change in y value over the change in x value, average rate of change. Now we've also spoken extensively about the idea that there is this thing called a tangent line. The tangent line just barely touches the curve, just kisses the curve at one point. And we can find the slope of the tangent line by finding the derivative of the function at some point. The mean value theorem says that if we have a continuous function on a closed interval a to b, and the function is differentiable, then there must be some point c for which the secant slope equals the tangent slope, or the average rate of change is equal to the instantaneous rate of change over the interval. Physically, we would say that the physical interpretation of the mean value theorem is that there is at least one point for which the instantaneous rate of change is the same as the average rate of change. That makes a lot of sense to us, especially when you think about the example that I used to describe this curve. Like, let's say you get in your car here in Pensacola and you drive yourself to Atlanta. You went a total of 350 miles, and let's say you did that in 5 hours. So you could say that you averaged 70 miles per hour. That doesn't mean you went 70 the whole time, that was just your average rate of change. Now, what the mean value theorem says that if your average was 70 miles per hour, you must have actually gone 70 miles per hour at least one time during that drive. And that absolutely makes sense to us, because if you're going to average 70 miles an hour, there's some slower parts, there are some faster parts. The only way to get from 0 to 80 is to go through 70 at least one time, maybe more than one time. So that's a physical interpretation. Now the mathematical part comes next. Mathematically, or algebraically, our job now becomes to find this point such that the slope of the secant equals the slope of the tangent. We want to find out where that happens. So that's our job in this section. To do that, we have to cook up the slope of the secant over this interval, and then find the slope of the tangent and solve for the value of c that will satisfy this equation. So let's first make the slope of the secant line. Remember, that's the average rate of change, so that would be f of 3 minus f of 1 divided by 3 minus 1. F of 3 is the square root of 3 minus 1, and f of 1 is the square root of 1 minus 1. 3 minus 1 is 2. So we end up with the square root of 2 over 2, because this term here, 1 minus 1, is just 0. So that is the average rate of change over the whole interval. Now, the instantaneous rate of change comes to us as the slope of the tangent line is the derivative at some point c on the interval 1 to 3. So let's find the derivative. The derivative would be 1/2 x minus 1 to the negative 1/2 times 1 if you want by the chain rule. That's the derivative of the function. However, you'll see that we needed to substitute c into that function, so the slope of the tangent line at any point c is 1/2 times c minus 1 to the minus half. Just a little change in variable there to let you know that c is some point interior of 1, 3. Now the question becomes, when are these two values equal? Where are they equal? What c do we need? So let's do that. Where does 1 over 2 square roots of c minus 1 equal the square root of 2 over 2? Right? The slope of the secant equals the slope of the tangent. So one thing that's handy when we set these up is the idea of cross multiplication. We multiply like this, if you will. That can help us get out of fractions. So if we did that, we'd have 2 square roots of c minus 1 times the square root of 2 equals 1 times 2, which is 2. Now we just want to solve for c. So one thing I would like to do is divide everybody by 2. And we see these constants there, just get rid of them. So that means we just have the square root of 2 times c minus 1, right? They're both in the rad party, so they can share that radical. Equals 1. And then we want to get out of the radical, in fact, so let's end the party with squaring the square root, and we square both sides to get rid of it and be fair. On the left-hand side, that leaves us with 2 times c minus 1 equals 1. And then solve for c. Regular algebra, 2 times c minus 2 equals 1. So 2c equals 3. Therefore, c equals 3/2. Then we have found the value of c that satisfies the mean value theorem. At c equals 3/2, the slope of the tangent line is exactly the slope of the secant line, square root 2 over 2. For one more example, with a little more depth, just a different function, different interval, let's find the value of c that satisfies the mean value theorem. Again, we'll need the slope of the secant line, which is f of b, which is 4 in this case, minus f of a, which is 2, divided by b minus a, 4 minus 2. We plug these values into the original function, natural log of 4 minus 1, minus the natural log of 2 minus 1, divided by 4 minus 2 is 2. We end up with the natural log of 3 over 2. That's because the natural log of 2 minus 1 is the natural log of 1, which is 0. There's the slope of the secant line. The slope of the tangent line depends on the derivative. We want to do that at some point c where it equals the slope of the secant. So the derivative of the natural log of x minus 1 is 1 over x minus 1 times the derivative of the argument, which is 1 in this case. And remember, we needed to have this as a derivative, a function of c, some point c, so we'll just make that change of variable, make that substitution 1 over c minus 1. Doesn't really matter if you want to solve for it in x, and it won't hurt my feelings. Alright, so now our job is to determine what value of c makes these parts equal. They have to be equal by the mean value theorem. We just want to find where. That means that we have 1 over c minus 1 equals the natural log of 3 over 2. To get out of these fractions, let's cross multiply. That would give us c minus 1, the whole denominator, times the natural log of 3 equals 1 times 2, which is 2. And we want to get c alone, so let's divide by the natural log of 3. It's just a number. Can divide by it all day long. So that leaves c minus 1 on the left equals 2 over the natural log of 3. And then to get c alone, we'll add 1 to both sides. So c is 2 over the natural log of 3 plus 1. A little bit ugly, but exact and a true value. It's still a number. If you wanted to put it in your calculator, you get approximately 2.82 as an approximation. So that's a place. There's a place on the number line we can find, and it is in fact on the closed interval from 2 to 4.